Assalamualaikum and good day everyone. So today is 5 June 2021 and time is 11:10 p.m. So we will continue with the week 13 of the lecture, which is the sequential MSI. Previously I've shared about the asynchronous counters. Okay, now we're going to proceed with the synchronous counter. Okay, so we only cover synchronous counter today. The design will be covered in the next lecture video. Okay, so without further ado, we turn to the page of this module, which is 174. Okay, synchronous counter or parallel counter solve the problem of ghost state. Remember, we have a ghost state in a synchronous counter. Before we reach to our targeted state, we have additional ghost state which is not intended. Okay, this one you can prefer from the previous lecture video on the ghost state. Okay, in synchronous counter, the clock signal is connected to all flip-flop. Okay, unlike in asynchronous, okay, only certain flip-flop is connected to the clock. Okay, in the case of synchronous, however, we connect all of the flip-flop with the clock signal. Although all flip-flop are clock, only the first or least significant flip-flop is wired to toggle all the time. Where this is question for you guys, where is the first or least significant flip-flop? Is it, let's say circuit is starting from the left to the right, from left to right, so which one is the first or least significant flip-flop? Is this the most left or the most right? So you guys can answer my question of that for that. Okay, other flip-flop may or may not toggle depending on the combination of output from the less significant flip-flop. Okay, the synchronous counter requires more support circuitry compared to the asynchronous equivalents. Okay, so what does it tell you? Means that synchronous counter is more complex. The circuitry is more complex or more complicated. Okay, so this is so you can see by here you already can extract the advantage and disadvantage of synchronous counter in comparison with asynchronous counter. Okay, so basic structure. Okay, figure 13.19, 13.20, 13.21 shows the structure for 2 bits, 3 bits, and the 4 bits binary synchronous counters. Okay, binary synchronous counter. Each counter starts from 0, increment by 1 every clock cycle until all flip-flops are ones and repeats. If you guys see, okay, this one is, it says 2 bits counters. Okay, 2 bit means 2 to power of 2. Okay, this is your number of bits. Okay, so if it's 4 means it can count up to 4, 0, 1, 2 and 3 in for the decimal. But for the binary is what? Okay, this one I think you guys should already know how to convert. Okay, so only this 4. Okay, and this one is 3, 2 to the power of 3. 3 is the number of flip-flops, so it can count from 0 until 7. 4. Okay, then you know, because this binary, you convert this to binary. Okay, so it's so easy. The same goes for this 4. Okay, a decade counter from 0001001 before repeating. You know, a decade counter is counting 10 times. I mean, counting for the 10 numbers. So here is actually from 0 until your 9s. Okay, then it count back to 0. The design of a decade counter is shown in figure 13.22. Okay, here later on we will see. For both 4 binary and decade counter, the longest propagation delay is between the output of flip-flop B and the input of flip-flop D. Why is that? Okay, again I read slowly so that you guys may understand it properly. For both 4-bit binary, this one 4-bit binary, and decade counter, which is on this figure, okay, the longest propagation delay is between the output of flip-flop B and the input of flip-flop D, between these. Also the same for decade counter, is between this is the longest propagation delay. Why is that? Because if you notice, we have two AND gate in between output of flip-flop B and the input of flip-flop D. So like I told you guys in the earliest lecture of the class, why sometimes, for example, right, sometimes we add buffer because for propagation delay. This is, however, in this case, there is propagation delay is due to this AND gate and also circuitry have their own delay and become more significant due to this AND gate in between. So this contribute to the longest propagation delays, okay, between this one. In this cut, the longest propagation delay from this, okay, between output B and output D because of the circuitry and also the flip-flop, okay, means due to this flip-flop and also due to the AND gate, okay. Counter operating speed, okay. Synchronous counter compute their next state in parallel. In parallel means if you compare with asynchronous, is one by one, okay. However, in synchronous, they will compute the next state parallel, all in one go, okay. That's why we call it synchronous, okay. Thus operate faster than asynchronous, of course. The propagation of the whole counter is the propagation delay for the slowest flip-flop, okay. So we just count the longest propagation we just count the propagation of the whole counter, for example this one, for the slowest one, okay. Since that, because each of them runs parallel, means all of them run at the same time, okay. Not the same as asynchronous, means not the same as asynchronous because they run parallel in this synchronous. So the propagation of the whole counter is the propagation delay for the slowest flip-flop, okay. There is no need to factor the individual speed of all flip-flop. Yes, correct, because all of them run at the same time. The propagation delay for a counter consists of the time required for the flip-flop to toggle plus the propagation delay for the output of the flip-flop to reach the next flip-flop, okay. To calculate the speed of the 3-bit counters, for example, in this for example in the figure 13.20, okay, 3 flip-flop here, okay, we have overall delay which is TF plus TG, okay. This is the overall delay, TF plus TG, where TF is the flip-flop delay, like I told you just now, circuitry or flip-flop, okay, have their own delay, and TG is the AND gate delay, okay. If you notice, there is one AND gate here, AND gate, okay. Okay, because we are now explaining based on counter in figure 13.20, okay. So where TF is the flip-flop delay and this one is the AND gate delay. It means that if you have two identical, remember my word, two identical AND gate, then you have two TG, okay, identical, it must be identical, otherwise if they are not identical means you have TG plus another one, okay. Now for the middle flip-flop, the other two flip-flop are faster as they do not have gates between their outputs, okay. This is correct because here we don't have any other flip-flop, or we don't have other gates in between, okay. So this is actually the one that contribute to the delays, okay, to the significant delays, okay. So for the middle flip-flop, okay, the other two flip-flop are faster as they do not have any gates between their output and the next stage, okay. This delay is the time required for the counter outputs to stabilize before the counter state is used to compute the next step. So the maximum frequency for the counter is then, since you know that F is equals to 1 over T, right? Roughly, okay. General equation, I think you learn everywhere, even since secondary school. So F equals to T, and here is actually 1 over TF plus TG, okay. So this way you get it. The frequency maximum is 1 over the flip-flop delay and also the AND gate delay, okay. Next, we're going to continue on the synchronous counter integrated circuit. Okay, now we are going to discuss about the IC for the synchronous counter. So several popular 7400 series asynchronous counter in IC are listed in the table 13.2, which we will see later on. These devices are closely related, with most pin assignment being shared, mean they have almost similar pin. Okay, so here you see these popular synchronous counter ICs. Okay, we have 74, 160, 61, 62, 63, 69. Then we have the count, decade, binary, clear method, whether direct, synchronous, presentable, yes, 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 and no, direction up, and this one is up or down. Okay, so we go to the 74 times 163 device. Okay, here, okay, which is count, binary, clear method, synchronous, presentable, yes, then direction, and direction is up. Okay, so the 74 times 163 device shown in the figure 13.23a, which we will see later on, is a flexible and useful synchronous counter to enable counting. Remember, to enable counting, both CEP and CET input must be given a high logic value. Okay, to enable counting. Okay, the counter has a synchronous reset SR, which clears the counter on a positive clock edge. Okay, positive clock edge mean from low to high of the clock edge side. Okay, now we have a synchronous reset also. Okay, which that job is to clear the counter. Okay, the output TC terminal count become high, TC become high when the counter reaches 1111, and this output can be used to enable other counter in a cascaded for configuration. Remember, right, if we want to have more counters, I mean to perform more counting, so we can cascade it. This one is also you learned from the previous lecture, okay, where it's smaller chip, if we combine in cascaded, we can obtain a bigger form of chip which perform the combination of all those small chips. So this is the 74 times 163 device. Okay, so what have been explained in the previous page is about the synchronous reset, the count enable, and also TC. Okay, this one we must give it the value of 1 to enable the count, right? Just like what it explained in the previous page. The counter can be initialized to any starting value, means doesn't need to start from 0, okay, by giving a low pulse at the PE input. Okay, you have your PE input here. Okay, we must giving a low pulse, okay, for that for the counter to initialize. Okay, and the required value at parallel input P3 through P0, the required value. Okay, from here, this one, of course, this is the least significant bit, and this one is the most significant bit. The 74 160, 74 161, and 74 162 are closely related to 74 163. Okay, these brothers. Okay, so I cannot if I increase the height, maybe you can see more of the full view of the module. Okay, I try it for a while. Okay, hopefully this is fine. Okay, yes, correct, but the word will become smaller, so it's logic. Okay, but you can have a more full view of it. Okay, all four devices use the same logic symbol and function table with few differences. They are all about the same, okay? The 74161 and 74163 here are binary counters. Okay, yes, correct. You can see they are binary counters. So the terminal TC output is high when reaching 1111. So it is true because 1111 is the maximum, because you can see this is 4 digits. You can have a maximum until 1111. You cannot have 10000, right? According to these pins, okay? But you can, let's say, you know, any design you can, when you do designing, you can do some creative arrangement in order for any circuits to perform something that we want as in the question. Okay, I think you guys learned it already. Okay, instead the 74 times 160 and 74162 are decade counters. Okay, say 160, I put double circle, and 74162 are decade counter. What does it mean? Decade counter means it only count from 0 until 9. Okay, which is, you can see which in the binary what is the number. Okay, the 74162 and 74163 are reset synchronous using the SR inputs. So you can see the 74162. Okay, let me erase this so that you'll be clear. Okay, the 74162 and 74163 are reset synchronous using the SR input. Okay, where is it? 74162 and 74163 as reset synchronously using the SR input here. Okay, meaning the counter is cleared when pin 1 is low on a low and on a clock edge. You see, when we have pin 1, when pin 1 is low on a clock edge, what does it mean? This is the pin number 1, pin 1. Okay, you can see the small one, but if I erase, you can see more clearly there is 1 here. Okay, so this one must be low. When this one is low, then we will reset. Okay, we will reset the counter. Okay, so means that the counter is cleared when this one is low on a clock edge. Remember, so this one is depends on the clock edge. Okay, on 74160 and 74161, this one differently. Okay, SR is called master reset. Okay, SR is called a master reset. Why we call it a master reset for these two devices? Because the counter is cleared immediately. They will be cleared immediately when this pin is low, without waiting for a clock edge. Okay, without waiting for the clock edge to arrive. Okay, because remember, because like this, you can see, right? The 74162 and 74163, they are waiting for the clock edge, even though this one is already low. In contrast, for 74160 and 74161, when the SR, our master reset, in this, they are called master reset, the counter immediately cleared, okay, without waiting for a clock edge. Okay, now we go for the next explanation. For example, okay, you can see, for example, you see, if you notice, this one, they have a lot of they have example where they say, given this, how to count from 0 until 1 or 0 until 9, please create a circuit or maybe design. Okay, so you can see they are having this kind of question now, and they are expecting this kind of answer. So in your module exercise, you can start to see this kind of trend, and please practice. Okay, because in your final, the question is on design. Okay, now implement a mod. This one is not really design, okay, but it is one step before designing, I suppose. So you can say it like that. Okay, the difficulty. Okay, now implement a mod counter mod 13 counter using a 74 times 163. So when they say about mod 13 counter, means it count from 0 until what? Okay, so this one you put the corresponding base 2, okay? I just want to shorten the time and also the page. If I want to put this maybe a lot of number, this one is so easy to explain using base 10, okay? But actually we are referring to base 2. You see, from 0 until 12 is actually 13 counts. 13 counts, okay? Now, because the 74, 163, the counter is cleared synchronously, we must clear the counter when we detect the value 12 at the output. True. Why? Because we can have other value than 12. For example, we can have value of 13 base 10. I mean, we can have the value of this one, okay, in the binary form, okay. To detect this number, we need to only detect high value of Q3 and Q2. Why? Okay, let me see. What is the 12? Okay, I know the number, but I just want to show it using calculator so it be clear. Okay, so now is 12, right? Decimal. So what is the corresponding binary? Is 1100. Am I correct? You guys can see this? I hope it's clear. Okay, so we have Q0, Q1, Q2, and Q3. So once it reach this 12, which is Q3 1, Q2 1, it need to reset. I mean, it need to count back, start to count back from 0. Okay. Now to detect this number, we need to only detect high value Q3, and Q2, just like what I explained, to an AND gate. Okay, to an AND gate, which will be activated when the count reach 1100. So here we need to see now. Okay, for example, okay, this is the circuits for this situation. So if you have 12, which is 1100, okay, so means you have 1100. What happened is that for the NAND gate is 111, but then invert mean you have 0 traveling until here. When 0 here, mean this one is activated. Okay, and as you see, this is 74 163 here, which is activated by using the clock edge. Okay, so you need to wait for the clock edge. Okay, then it will then reset. Mean after that, when this one is low and the suitable clock edge is achieved, is arrived, so then it reset to count back from 0 again. Okay, now the output of this, then we do not need a count to connect Q1 or Q0 because the counter of count of 11 is reached before the other values. So this one is don't care, so we don't care about this. I think this is quite straightforward, okay, to understand. Okay, next, implement a counter that goes through the value of 2 to 8 using 74 163. Okay, if you see now, it need to count from value of 2 to 8. Remember what I told you guys? When we didn't mention the base, it is usually assumed to be base 10. So don't ask this repeatedly during exam or question, okay, because it's clearly that if you ask this, you don't understand, because I repeatedly explain in the class. If the number without any base mention, it is a base 10. Okay, so avoid asking things that showing you didn't understand. Okay, because this is critical if up until now you still not understand about this. Okay, so here it need to be able to count from 2 to the base of 10 to 8 to the base of 10, which is the what is the equivalent number. I just want to show using this because it's, we don't, it's simple to prove to you guys. Okay, 2. So what is the binary equivalent? How about 8? 8 the same, I know, but I just want to like to press them. Okay, then you see the binary, what? 1 0 0. Okay, so you have 1 0 0, means it start at 1 0 1 0 and it should end at 1 0 0 before it reset to count the next, count again at 2. Okay, so solution, place the value of 0 0 0, sorry, I'm sorry, this is a bit of error, okay, 0 0 1 0, okay. So place the value of 0 0 1 0 at the parallel input. This is the first value that we assign, okay, which is 0 0 1 0, corresponding to 2 base 10 right here, okay. At the parallel input, load P3 to P0 into the counter by placing 0 at the PE input. You see, we place a 0 at the PE input, okay. Load P3 to into, okay, by pressing 0 at the PE input when the counter output at which happened on the first clock that Q3 is 1, okay. So means we okay, so it means that it should stop at here 10 at 8 before it count the next bit, okay. That's why we put here 1 0 0 0, okay, because it first reach the maximum with the number with the combination with Q3 equals to 1 and the rest is 0. So we put here 1, this is inverter gate, then 0. Then what happens? 0 go all the way to here, okay. Then it's activated the PE, okay. Okay, which happened on the first clock that Q3 is 1, okay. Simply connect Q3 to an inverter, then connect the inverter output to PE as shown in figure 13.25, okay, here. Other counter can safely be ignored because the value 100 is reached before other values, because the first value of 1, this you have is actually 1000. Okay, this is the first value, this is the second value, okay. The first value, the reach that, I mean the counter at, okay. So that's why we only put attention to this Q3. We don't put attention to the rest, because before it reach this value or the rest, it's already set to count from 2 again, okay. And you see there's a clock edge here, okay, because it is synchronous and it's based on a clock edge as well. It's need to consider the clock edge also, okay. Okay, this one you guys can try to read, okay. It's almost the same. We have a lower nibble, upper nibble, okay. Sit down and try to understand properly, okay. So because you can get this in your exam, okay, implement a mod blah 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 using blah blah. So it's better that instead of I spoon feed all the information, you try to find it yourself, okay. And of course it's already provide the explanation, you just need to try to understand, okay. Now the next is 74 times 169 device, this one, okay. Which is, you see, binary, clear method, list one later on, presentable, no, and direction up or down, okay. Now the 74 169 device is a bidirectional counter closely related to our the sister 74 163. Bidirectional means it can count up or count down, means from small number 1 to 3 or down 3 to 1, for example, okay. So this counter is called an up or down counter. So refer to figure 13.27. Hopefully we can yes, we have the space to actually cover all the pages. Good, okay. So refer figure 13.27. Most pins on the package have the same function except that we have additional pins, which is the U/T. When U/T is given logic 1, okay, when this one given logic 1, it will count up, means from the small number to the bigger number, okay. But when it is given 0 instead, it will count in reverse, which is from the bigger number to the smaller number. The TC, CET and CEP pins are active low, okay, it does not have an input to clear the counters. Okay, so this circuit doesn't have input to clear the counter. Okay, so now we see the example. Create a Knight Rider like sequencer using 74169 and a minimum of extra device. Okay, I don't really know why this example is being used, because if they mention Knight Rider means you need to have a pre-information, mean you need to have existing information on Knight Rider. I also didn't know what is Knight Rider. The Knight Rider is a car in a TV series from a long time ago. The car has an LED pattern that sweeps back and forth. Okay, means sweep back 0, 1, 0, 3, 1, 2, 3, 3, 2, 1, 0. Okay, to create this pattern, the counter has to come up until it overflows, then count down until it underflows. Okay, just like the words here, sweep back and forth. Okay, and so on. The counter output is connected to a decoder. You see, this is a decoder. We can use the TC output here to detect the overflow, or underflow. Okay, you can see right just now, right? The TC here is if L, it means count 1 0 1 1 1 to count up, and count 0 0 0 to counting down. Let's go. Okay, at the pin 15. Okay, TC output to detect the overflow or underflow condition and use it to toggle a T flip-flop. Okay, and use it to toggle T flip-flop. You can see where is the T flip-flop here. In this figure, where is the flip-flop? Here, correct? This is a flip-flop. Okay, we use it to toggle T flip-flop. Alternatively, we can use the first and the last pin on the decoder, to set and reset an SR latch. Okay, this one is SR latch. Okay, but it's not sorry, this is not a flip-flop. Okay, but it's a sequential circuit. Okay, sequential circuit, which is the SR latch. Okay, means here you can use either T flip-flop or you can use SR latch. This example is actually using a SR latch. Okay, so with that, we finish about this synchronous counter. We'll cover on design of a synchronous counter in the previous lecture, in the next lecture. Okay, Assalamualaikum and good day. See you soon.